into statistical modeling in overview. Like for instance, we basically want to explain, okay, even though we do some form of prediction too in statistics, but I just wanted to be aware that, you know, statistical model do not have a very strong power, predictive power compared to machine learning algorithm. And the machine learning algorithm does not have an explanatory power at all. No explanatory power at all, you know. So now statistical modeling in overview. Now, in the outline, I'm going to talk about modeling. The essence of modeling, of course, when I say modeling, I'm referring to statistical modeling. Does that make sense? Then I'm going to walk you through 4-step process when you decide to, use statistical technique in your research or in whatever analysis you want to do. Okay, so I'm going to go into modeling now. I think the other time I actually I define what we mean by model, right? I define what we mean by model. I said, mathematical, you can call it mathematical or statistical, okay, representation, okay, representation of reality. Of course, we basically want to model reality. The facts remain that if we want to model reality, of course, we actually need to we're going to be working with notations. We're going to be working with equation because the model that we have is basically going to comprise of notations. It's like trying to trying to actually use denoting the word like with notations. That's exactly what we mean. So the process of doing that is what we call modeling, okay, which means we are modeling. Now take a look at this. We actually want to describe reality. I'm going to give you an example of describing reality. When you're driving, right, and you want to use GPS, the GPS is a model. What you see on the GPS is not the exact reality, but it's an approximate, right? Approximate reality. And because of that, models is not the same as reality, but it's an approximate reality. And the reason why model is not the same as reality is because even with the best model, you cannot extract all information. I think I told you something the other time. Initially, we do not have knowledge. We are here to see, to acquire knowledge. If I want to understand what is happening in the world, I need knowledge of the world, right? Like I said the other time, I need knowledge of the world. The knowledge is going to come from where? The knowledge is coming from information that I got, right? Where is the information coming from? The information is coming from data. It means I need to go to the population. I need to collect data, relevant data, not just data, okay? Relevant data. And when I collect data, the information that I need is not readily available. I'm going to say that again. This information, the moment you collect data, you don't have access to that. But what is the only way to have access to information in the data? You're basically going to use model. You need model. Okay. And you know what? The best model will not extract all the information. There's always going to be information loss. I'm going to give you an example now. Take a look at this guy, right? I want to drink it, right? They say, what do you think I'm interested in? I'm interested in the liquid content, right? The liquid content is information, right? But the whole thing is the data, which means every data is contaminated. Every data is contaminated. So what do we, using module now, we're actually going to use module to extract signal. What is signal? Signal is information. There's something is going to go into a trash. When I drink the liquid contents, what will happen to this guy? He's going to go into a trash. That's an information loss. Does that make sense? And that's actually explain the reason why model is not the same as reality. But you know what we want to do? We acknowledge the fact that model is not the same as reality, but a very good model is the one that have a minimal error. Because we want to make sure that whatever that go into trash is minimal. Does that make sense? Okay. So a model is a simplification of reality. We just want to simplify reality. Why do we need to simplify reality? Because reality is complicated. I just wanted to know that. And when you look at reality that is complicated, you may not be able to solve any problem unless you have to simplify reality using a model. And of course, something that is complicated, you want to simplify that, then you should be ready to lose information. We don't care about losing information, but provided the information that we lose is very, very minute, very, very negligible, we are fine. Okay. Models help us to understand reality. I just mentioned that. Then, Judge Box said, and I quote, all models are wrong, but some are useful. Do you know why he said that? Because if you are investigating, if you ask a question, if you ask this question, if you ask this question, is a model true? If you mean the whole truth, then the answer is no. Because a model cannot be completely true. Does that make sense? And that was why Judge Boss said all models are wrong, but some are useful. Okay. And why is it that some are useful? Because those ones that are useful are those ones that we've been able to validate. Like because every module has assumption. Every module has assumptions. And you know what? Assumptions lead to limitation. Okay. Now, if I want to know how valid is a module, how valid is a module, if I want to investigate that, then I need to investigate whether assumptions hold. In this course, I'm actually going to be walking you through some statistical model. Every statistical model has assumptions. And let me tell you this, assumptions that we have centered on the error. Look at that. Assumption that we have centered on the error. Because we want error to behave well. Okay? How can error behave well when it is very, very small? Any question? You good, right? Okay. Now, the suitable complexity of models can depend on the purpose. A model can be simple, can be complex. The only thing you just need to identify in every situation is just like understanding the problem. Okay, situation where you are supposed to use a simple model. If you use a complicated model, there's going to be a problem. Where you are supposed to use a complicated model, if you use a simple model, there's going to be a problem. Therefore, there should be an agreement between the model, okay, and the data. the module and data must agree. Does that make sense? Okay, because in this course, we're going to be talking about like linear module, non-linear module, some simple module, some complicated module. We don't just apply any of that. We look at the situation. We look at the purpose. And that was why we said, depending on whether we want to understand or the prediction. Now, it's an example of a module. It's an equation. Okay, there's a partial differential equation. Take a look at that. It's an example of a module because this is depicting reality. Okay, and we believe that the moment we solve the problem, we solve the equation now, of course, maybe we've got the solution to the problem. Okay, now take a look at this. Anything can be module, whether from business to economy to medicine, agriculture, anything at all can be module. The only thing is we just need to get the right module, because when you are using the wrong module for a given situation, you're basically going to mislead. And therefore, understanding of the problem is very, very crucial. Okay, somebody said, my research system is complex and cannot be described in terms of any model. That is not true. No matter the complexity of research, it can be modeled. For any given problem, there's basically going to be solution. But the problem we have is that maybe we've not located the solution, but the solution is somewhere. Does that make sense? And that's why it takes some researchers years before they could figure out a particular problem. It doesn't matter the number of times it takes. Okay? Now we'll be talking about model, right? We got different kind of model. Of course, we have some models in physics, some models in economics, some models in mathematics, but we want to focus on statistical model. Okay, we want to focus on statistical model. And when we are talking about statistical model, then we can rule out probability distribution. You know why? Every statistical model is probabilistic. You know why it's probabilistic? Because when you specify statistical model, there's always going to be a random part. Okay? There's always going to be a what? There's going to be a random part, which I'm going to show you now. Take a look at this. When you collect data equal to model plus the error. I told you the other time, every data is contaminated, right? Look at that expression. That means data is contaminated because data equal to model plus the error. Now, when it is contaminated, the efforts, our effort in statistics is actually to filter out the noise. Error is a noise. Noise is the same thing as the error. How do we filter out the noise? And because of that, if you have, if you look at what I just, what I wrote now, you have data equal model plus the error. Okay, data equal model plus the error. The model here is deterministic. The deterministic part. This is a random part. I want you to take a look at that now. Now, if I now want to use notation, if I write y equal f of x, okay, plus the error, what am I trying to say here? For instance, if I'm looking at the relationship between y and x, Maybe my y is actually volume of sales. And maybe my x, here, the function of s, I can have, one input, two inputs, and so on like that. Let's assume that I only have one input, and I have amount spent advertising. Okay. Actually looking at the relationship between the volume of sales and the amount spent advertising. Okay. Now, this is I'm going to write this as a model. But what does it mean? This side, this is the functional form, because this is a function of amount spent advertising. And this side is a random part that we call the error. Now, this, if on this one, I'm actually going to have total variation. We're going to have variation around that. Here, I'm going to have explained variation. Explained variation. And here, I'm going to have unexplained. Unexplained variation. It means amount spent advertising cannot explain 100% in the response. There's always going to be something. There's only going to be a factor that we don't consider that also have effects on the response. That's what we mean. There's always going to be a random part. Does that make sense? Which we call the error. Even though we are concentrating on these two variables, statisticians acknowledge the fact that, we have a nuisance variable that we don't consider that also have effects on the response. For instance, it is not only this guy that can make you to sell. There could be other factors as well, right? And if you don't consider those factors, why are you not considering them? You are having an assumption. You are having an assumption that the reason why you don't consider them, they have very small effects. And that is why we call them unexplained variation, which means it is not all the variation in the response variable, the predictor variable we explain. Does that make sense? So that's exactly what we're trying to say there. Okay, what is the essence of statistical modeling? You will be better equipped to choose the right model for your needs. We got different kind of situations in life. We got different kind of problems we want to solve. Therefore, when you understand statistical modeling, you will be better equipped. You'll be able to choose the right model for your data. Now, you'll be better able to prepare your data for analysis. Before you analyze, you need to first put your data in statistical standing. I'm going to say that again. There's something that we call data preparation. Data preparation. Okay? You prepare your data for analysis. Okay? That's exactly what we mean. And not only that, after preparing your data for analysis and you carry out analysis on your data, what are you going to do at the end of the day? You're basically going to be a better communicator. And right now, I'm communicating because I'm already equipped. I'm trying to give you information about the right statistical methodology to use. Any question? If, like I used to say, if anybody is struggling, please let me know. If I'm talking so fast or I'm talking so slow, please let me know. Okay? Thank you. Now you understand what we mean by essence of statistical modeling. Now, if I want to apply statistical model, we actually have 4-step process, which I'm actually going to walk you through now. The other time when I was trying to differentiate between explaining or predicting, right? I said statisticians, economists, psychologists, in fact, scientific community in general, they normally focus on explaining, right? Because they want to understand the world. They want to explain the world. And when they are doing that, they will focus more on the theory. If you look at the tension that I discussed with you the other time, now in focusing more on the theory, it means if they want to start, then we have to start by choosing a functional form for the model. Look at this FFS here. They're going to decide on the functional form at the beginning. The functional form, this is what I mean. Functional form, right? They will decide on whether they're going to use linear, or non-linear, and so on like that. They're basically going to use their experience. Statistician, normally starts by specifying their model. I'm going to say that again. Statistician starts by specifying model. That is step one. Choose a form for the model. Before you can choose a form for the model, then of course it means you are guided statistically. You don't just choose a form. Then it means probably you've reviewed literature. Because you're basically going to use what I call the principle of subjectivism. You're going to base it on experience in the field. Now, after choosing a form for the model, then you now need to fit your model to the data. Don't forget, you've collected data, right? And you're basically choosing a functional model for the data. And you now want to test hypotheses, okay, to see, given the data, you want to test an hypothesis. But let me tell you this, before you can get anything reasonable, you got to make sure the state of the model must be the same as the state of the data. I'm going to say that again. The state of the model has to be the same as the state of the data. When data require linear relationship, what they are trying to tell you, use a linear model. When data requires non-linear relationship, use non-linear model. There must be an agreement. Okay? Now, if you look at the first step, right? You choose a form for the model, right? And the second one, you fit model to the data. And don't forget the other time, I said, when you collect data, you don't have access to information immediately, right? You need to fit model to the data for you to be able to have access to the information in the data. But you can only get reasonable information from the data if you have chosen the right model. If you don't choose the right model, you're not going to get any reasonable information. So part of what I'm going to be doing in this class is just to guide you on how to choose the right statistical model for a given problem. Does that make sense, right? Okay, now you see step 2, right? Now we're going to go to step 3. In the step 3, we're actually going to do what I call a validity test, where we want to assess how well the model describes the data. Why do you choose the model in the first place? You want the model to describe the data well. Because how are we going to know whether the model you have chosen will do a good job? Then you need to do, that's step number 3 is called evaluation. You are evaluating the validity of your model. And let me tell you this, what you're going to see us doing in evaluation of a model, okay, what you see us doing is what I'm going to call diagnostic We call it regression diagnostics. You know, if a doctor has treated a patient, how do you think the doctor will know that the patient has recovered? Maybe before the treatment, the doctor will measure something, right? Maybe the doctor is interested in, maybe the patient has high blood pressure, right? And before intervention, the doctor will measure maybe the person had maybe like 125 or 120. And if the doctor wants to know whether the intervention has worked, what is he going to do again? It's basically going to measure that BP. And if the BP now goes down to a normal level, the doctor can now say, yes, my intervention worked. We do the same thing in statistics. We call that regression diagnostics, where we're going to do diagnosis of our model. It is not all model that works. We need to investigate model. But the question remains, what do we investigate in a model? Can somebody tell me? When you want to investigate a model, what do we investigate? We investigate assumptions. We investigate this guy because you know why? Every model has assumptions. And as assumptions centered on error. Look at that. And there's a say, a model is as good as assumption put in into a model. Look at that. If I really want to know whether a model works, then I need to investigate assumptions underlying the model. If assumption hold, then I'm going to be celebrating. Does that make sense? So that's exactly what we mean. So we're going to do a lot in that, in this step, and I'm just trying to tell you now. Now, if our assumption hold, the other time when Judge Box said all models are wrong, but some are useful, okay, I try to revise that. I said all models are wrong, but we can make some to be useful and safe. You know how we can make them to be useful and safe? By trying to make sure that they follow assumptions. Otherwise, if we investigate assumptions and assumptions are violated, then it means I cannot use that model. I need to think about another model. Or something needs to be done. Like in this course, I'm basically going to walk you through when assumptions are violated, what can we do? I'm also going to tell you in this class. We call that transformation. Because it's just like I have a child, and maybe the child is misbehaving. Then what can we do to make sure he's behaving well? We're going to transform the child, maybe by talking, speaking with her, this, that. We also do that in model too. Does that make sense? And if we transform and it doesn't work, then we have a way to look for an appropriate model that works. Do you know, it's not as if our models are failing us. Our models are not failing us, but we are the one that we're not doing the right thing. I've seen situations in the past where some researchers conducted research and their recommendation did not see the light of the day. Their recommendation did not come to pass. You know why? Because they used wrong model. Because they failed to investigate whether assumptions hold. Because they forgot the fact that we live in a stochastic world where model can never be exactly as reality. Does that make sense? Now, the last thing we're going to do when assumption hold and we are celebrating, then the next thing, use the model. We're going to use the model to address the question that motivated collecting data in the first place. Does that make sense? Before you go into that step 4, you got to make sure step 3 hold. assumption hole. Now, what makes a model? What makes a model good? I think I just talked about it. I said there are generally two different things that we want from our statistical model. Don't forget, that is what I described the other time. Let me tell you this. Whether you are talking about statistics or you're talking about machine learning, they are variants of statistics. I'm going to say this again. It's just like you have a COVID, we have variant of COVID, Omicron, Delta, and so on like that. All of them, they are all statistics. Now, I said first, we want to describe our data. Don't forget, describing is not prediction. You know that, right? Okay. We want to describe our data well. Okay. That is, we want it for you to be able to describe our data well. Then it means you have a minimal error. That's what it means. That doesn't mean there's no error at all. There's going to be error. You know that there's going to be error. Okay. And I said another thing. Second, we want to generalize. You know the meaning of generalizing? You want to make a prediction. We want to generalize, well to new data set. That is, we want the error to be as low as possible when applying to new data set. And look at that last statement. That last statement actually justify what we did on Wednesday. Look at the last statement. It turns out that these two features can often be in conflict. That was what we talked about. To explain is different from to predict. I told you that is what we know there. There's a conflict. And that's why you need to decide on what you want to do. What is your intention? Do you want to explain? Do you want a model that can describe your data? Or do you want a model that can generalize? There's a difference between model describing your data and model generalizing. The two of them are not the same. You got to decide. Does that make sense? And that what we do in scientific community, I think I remember a friend, my economist friend, told me one time, he said, if I can explain any phenomenon, I should be able to predict any phenomenon. The answer is no. And I gave you an example the other time. If I know how car works, if I know the way car works, and that does not mean I will predict where the car will go. The car, if I want to predict where the car will go, then I need a driver. Okay. Let's now talk about fundamental terminology, because you need to get yourself familiar with notations in this course. That's what I want to talk about now. I think we have like 10 more minutes, right? Okay. Now, the observation unit, and we call that, that is a unit, that you recorded data on. It could be people, it could be objects, in fact, it could be countries. If I'm comparing, living conditions of companies, of countries, country become observational units. It could be schools. It could be counties in the United States. Okay, now the next thing is variables. When you have a model, right? Just like the one I actually wrote the other time, right? The model is basically going to look like this. Y equal f of x plus the error. This is the functional form that I'm talking about. Right? Now, your y is a response variable. We also call it dependent. Okay? Your x is independent variable. We also call it explanatory. We also call it predictor. So take note of that. Okay. Now, when I talk about variables, we're talking about characteristics that are actually measured or recorded about each observational unit. in my hospital, maybe my observational unit are the patients, you know that, right? And maybe I want to measure something from them. What variable? Maybe I want to measure BP, blood pressure. That's a variable. Why is it variable? What do we mean by variable? What do we mean by variable? Anything, variable is anything that is liable to change. Don't forget, we are in a stochastic world where what I measure from this individual is going to be different from what I measure from the other individual. That's a variation. I think you know that, right? Okay. Now we got two types of variable. I think I just explained that. Explanatory variable. Okay. The explanatory variable is the variable you can manipulate and you observe its effects on the response. Symbolically, we normally denote that as X. It could be one, it could be more than one. The response variable is actually a variable that depends for its value on another variable. Oh, I want to determine the GDP. I remember what I work on in my bachelor program. I work on what is it called? Effects of exchange rates, consumer price index, and inflation rate on the GDP of Nigeria. That was what I work on my bachelor project. So take a look at that. That's what we mean. So you need to be able to identify what is your explanatory variable, what is your response variable. Oh my God, what is next? Okay, so what we're going to do next time, we're going to talk about the scalar plot matrix, because now we're going into a relationship. We want to go mathematical now. Now that you understand, the notation we use for response variable, the one we use for explanatory variable. Now we can now start using mathematical technique or statistical technique. So this is what we're going to do on Monday. Any question today? Any question? Okay, you know what I needed to do. At the beginning of the semester like this, I normally adverse opinion. I cherish feedback. Okay, I need you for this week, based on what we did on Wednesday and what we did today. I need you to send me a message. I need you to rate your understanding. Okay, rate your understanding. Now, rate your understanding from 0 to 100%. If your understanding is less than 100%, you need to include in your message what you want me to clarify. Does that make sense? Like I said, I always want to hear from you. Problem disclosed, is problem solved. Sorry about that. Maybe I'm going to minimize the use of chalk. Sorry about that. Oh, shut up. I don't have. What do you care? Do you drink this one? Do you care? You can have it. Yeah, you can have it. You're welcome. Okay, so make sure you enjoy your weekend. Bye for now, everyone.